¿Puedes quitar?
No veo, pues.
Okay, so welcome to today's seminar. So you have Anna Asenjo from the University of Columbia. So please, Anna, when you want, start.
Thank you so much. Thanks for having me here. It's a pleasure to visit the SIG. So today I'm going to tell you about two recent pieces of work that are a bit different in topic, but they share kind of well, they have something in common, that is correlated decay. So if I think of what's going on in our field, in the last few years or even decade, one thing that is very easy to notice is that there is a huge diversity in the goals or applications in quantum science and technology. And some of the applications range from quantum computation and quantum simulation to also pressure measurement or the development of distributed networks for information. And so there is not only a huge diversity in applications, but also there's a huge diversity in systems. So some examples in this slide include arrays of neutral atoms and also superconducting qubits. And it's not only that there is a lot of types of particles that can serve as qubit, there is also a lot of type of particles that serve as a mediator of interactions between qubits. So these particles can be photons, or basically the bath can be the electromagnetic field. But one can also tailor the vacuum of the electromagnetic field, changing the dispersion relation of the optical dispersion relation, such as in this work where they place emitters in a photonic crystal. Or you can completely forget about the electromagnetic field vacuum and just think about other types of baths, such as collective excitations in a material, like phonons, magnons, and so on and so forth. So then, again, maybe recapping, we have a different set of goals, different set of qubits, a different set of paths. And instead of thinking of what makes each of these systems, we think what they have in common. I think there are two key pieces. The first one is that in all of these examples, the aim is to control large ensembles of qubits. And the second common feature, which is actually an issue that arises because we want to control these systems, is that they are naturally open. And so from a fundamental perspective, systems are naturally open in the sense that they are intrinsically coupled to a bath. And this bath, even if it's vacuum, it has fluctuations that cannot just be switched off. And that's actually very good because we harness these vacuum fluctuations to mediate coherent interactions between qubits. And that's actually what gives rise to the whole fields of like quantum computing, sensing, metrology, and so on. So I like to highlight two recent pieces of work where vacuum fluctuations are harnessed to realize, well, they are explored in atomic clocks and also in arrays of Rydberg atoms. So the first paper this is not working. Oh, what? We try. Well, that first paper is a paper from the group of Q&J in Gila, where they have a dense optical lattice of atoms. And this dense optical lattice basically deals dipole-dipole interactions between the atoms that they can measure in the clock. And then this other paper on the right, which is just an example of actually 3 papers that came out together in Nature last year. They harness vacuum fluctuations to realize spin squeezing in Rydberg arrays. And so in contrast to the more typical examples where we place atoms in a cavity, these arrays are in free space and the interaction range falls as 1 over r cubed, yet it can be used for producing a spin. Okay, so these are two examples of many where the vacuum mediates coherent interactions, but it also means that you cannot, because there are these coherent interactions, naturally there has to be also dissipative interactions. And these dissipative interactions may also be long range. And once you have that, then this is going to lead to decay. And if you have many particles, this decay is going to become correlated, or has the potential for becoming correlated. And then if you think about, what is the role of correlated decay, you can think of it being really a terrible thing that you have to avoid by all means, or it can be something awesome. So let me just tell you, what are the two sides of this coin. So if you care about, for instance, doing metrology or quantum simulation, you may want to, correlated decay is bad because it's going to limit the time that you have to perform your experiment, either to prepare a state that is interesting, and also to use that state for something, because this state is now going to have a reduced lifetime. For quantum computation, correlated decay is potentially even worse. This is a recent paper in the group of Misha Lukin, where they are looking at decay from the computational basis in a Rydberg atom. And this decay happens because of spontaneous emission. So now if this decay becomes correlated, this may violate the threshold theorem for quantum error correction. And now you're going to have an error that scales up as we increase the system size. It's not constant anymore. So it doesn't mean necessarily that you cannot perform quantum error correction, but definitely it makes things happen. On the other hand, correlated decay is very useful if you want to extract energy, for instance, of a system very rapidly. So for instance, if you want to realize a source of light that is efficient. And it's connected with some ideas such as the super-radiant laser, where we have an ensemble of atoms that are incoherently driven. Above certain threshold, this ensemble starts to radiate coherent light. And this coherent light, the intensity goes as 1/m². And also the thresholds at which this lasing occurs depend on the number of particles. And this again, because decay is correlated. And then maybe more generally, there are many examples in cavities where people have studied out of equilibrium as in driven dissipative phase transitions. The properties and the thresholds for these phase transitions depend on the system size, okay? And therefore on correlated decay. So this is an example of a transition from magnetized to super-radiant in not in a cavity, but in free space by the group of Antoine Breuils, where in this case they drive coherently the disordered cloud of atoms, and they claim that this transition that occurs can be brought by looking at the intensity, and in particular the scaling of the intensity with system size, the forward direction. Okay, so if instead of thinking about all of these systems, their particularities, how they are all different from each other, and so on, we think of, can we say something about all of them at the same time? Wouldn't that be nice? So that's basically the topic of the first part of my talk today, and actually the main part of my talk, which is what is the maximal decay rate of a quantum system. Okay? So basically the idea or the goal for this talk is to find a scaling laws for correlated decay with system size, which for me is n, the number of particles. And the hypothesis is that the environment and the arrangement of this particle is going to change this maximal decay rate. And the result is that we'll find simple universal scaling laws that can be obtained for a broad class of Markovian systems in an easy fashion, which means if I give you the recipe, you can find the largest decay rate of your system in a computer in a time that scales only for polynomial systems. And if you want to know more details, you can take a look at our recent paper, which we posted 2 weeks ago. Okay, so the first thing that I'm going to tell you about is what happens for generic Markovian systems. And even though this is a problem involving dissipation and decay, we're going to go about solving it by mapping it to finding the ground state of a Hamiltonian. The second thing is I'm going to use the scaling laws derived in the first part to tell you something about the maximal decay rate in atomic arrays in free space. And then the last part of the talk is switching gears a little bit. It's an example where correlated decay is actually something very useful, and it serves as a way to do transition quenching. So basically, if you have a system with many possible ground states into which the system can decay, via correlated decay, you can suppress decay into many of them and just have all the population in the dominant ground state. Okay, so also I should say that if you have any questions, please interrupt me, because then I just don't run on and on for an hour. So that will be nice. Okay, so then let's start by the beginning. And so we're going to consider a quite generic Markovian many-body dissipative system formed by spins or qubits, two-level systems. And I'm going to describe it via a spin model with dynamics governed by a Lindblad master equation of this form. So this Lindblad master equation has two pieces, one part that is Hamiltonian, and it conserves the number of excitations. And this last constraint I can release, but just for the purpose of this talk, I'm just gonna keep it for now. Okay. And then importantly, this system is open, so there is dissipation, and this dissipation is captured by the second part of the equation. And this dissipation is collective, as it depends on particle I and particle j. And the dissipative couplings between particle I and particle j are given by gamma ij, which I can build as an n-variant matrix that tells me how these particles dissipatively talk to each other. And the only constraint I need to put in this equation or for this matrix is that this matrix is positive semi-definite. And this is just to generate a completely positive trace-preserving dynamics. Okay, so then it's always, within my freedom to change bases. And so let me just change bases to the collective basis. For now, I have diagonalized this matrix. I write this in terms of the collective transition rates that are eigenvalues of the matrix. And these C's are collective decay rates, which are collective jump operators that act on all particles in principle. And these eigenvalues, because the matrix is positive semi-definite, are guaranteed to be 0 or larger than 0. And this is because they represent decay. So something decays at a rate that is 2 megahertz, not at a rate that is minus 2 megahertz. Okay.
Sorry.
Yes.
Are you seeing here some kind of mode structure like in the solvable system, or is it just so
mode structure?
So is C dynamic,
yes.
Right? Are there projectable ways?
It's kind of generic, so I will talk about specific cases next. Yes, but this is, you give me, if you want microscopically, you give me some system, you integrate at certain degrees of freedom. This yields the master equation that I told you about, and then I can kind of perform this transformation of bases. Or I can also postulate this as well, just by assuming that this is a linear map.
But what I was asking maybe is n, is it exponential or?
Oh, this n is literally the number of particles. Yes. Yes. Okay, so then among these many eigenvalues, there is one that is the largest one, that is gamma max. So the largest eigenvalue of this function. Okay, and I just single it out because it will appear. Okay. Okay, so then if you now have this master equation and you try to find the dynamics, kind of some arbitrary dynamics that you are interested in because you are given a problem. Theoretically, this is a hard problem. And this is because typically this dynamics explores, a large Hilbert domain, unless there is symmetry. So an example where there is symmetry is if you place all particles in a cavity or just by hand, you take this gamma ij and you make it all equal for all particles. That means that you can exchange the particles, I and j, and the dynamics remains equal. And so this means that you are basically confined to a small subspace in the Hilbert space, that is the states of permutation symmetry. And an example of this is, for instance, the superradiance. And what happens there is you go down, and it's very easy to compute these dynamics, and along the way you hit the states whose largest decay rate, or states of very large decay rate that scales quadratically with step size. Generically, the dynamics is more complicated. This is, me drawing by hand some generic dynamics of like getting lost in the Hilbert space. And And so can we do, if you think about this type of problem, it involves typically many particles, it involves long-range interactions, it's out of equilibrium, and many cases we care about dynamics. So when you add these things up, this means it's a hard problem. And then, of course, you can maybe make approximations. And people have worked on approximation methods such as cumulants, phase space methods, and so on. But you can also use matrix product states. But in many cases, these methods are also limited with respect to how large of systems they can describe. Some of them are unreliable. So sometimes cumulants explode and give you just completely wrong answers. And then I'd like to highlight that for me, the major drawback is that they are, it's hard to get intuition from just doing numerics. So actually, a large part of this talk is what can you say about these systems without doing any numerics at all. Okay, it's just analytic. Okay, so then what we want to compute is the largest decay rate of a quantum system. And so the first thing is what is the decay rate? Well, if you give me a system and some state in this system, I can always compute the instantaneous decay rate by looking at what is the rate at which the system is losing population in the excited state, which is the first part of the equation. And then once you want to compute this expectation value, you use your master equation, you do the math, and you find that this is the, you have to compute the expectation value of gamma ij, sigma plus I, sigma minus. So you take a look at this, and it actually looks like a Hamiltonian. So then I'm just gonna say that this is just taking the expectation value over that state that you gave me on this auxiliary of dissipative Hamiltonian. And actually then to find the largest decay rate, it is to find the largest eigenvalue of this Hamiltonian or the ground state energy of the minus Hamiltonian. So this is as if you had a closed system and I ask you which is the state of minimal energy. You would say, well, it is the ground state. So for an open system, there is an equivalent concept that is, the state of maximal decay rate, which I'm going to denote as R star, is the, is that state over there. That is the largest now eigenvalue of the Hamiltonian. Okay, is this clear? Should I? Okay, good. So then, before I proceed any further, let me just tell you about two limiting cases. The first one is what happens when you have completely independent particles. So now if these particles don't talk to each other, this decoherence matrix gamma is just, it has only terms in the diagonal. All the other terms are zero. And then it is very easy to find that the maximal decay rate is L gamma 0, such that the decay rate per particle is constant, is gamma 0. Then let's go to the opposite case, which is all-to-all interactions, as if the particles would be in a cavity. In that case, there is this permutational symmetry. This gamma ij is a matrix full of ones times the local decay. And then I can map the problem to the problem of decay. And I know that the largest decay rate is a decay state, or the state of largest decay is a decay state at half excitation, where the decay rate scales as n squared. And so these two situations are trivial. And the question is what happens in between. So what if now you're in some other environment where the interaction range is not all-to-all, but for instance, a power law, or whatever you want to give me. And then I arrange my qubits in some particular geometry. All these features are encoded in this gamma matrix. And I want to know now how these features determine the largest decay rate of my system. Okay, so then I told you that, well, this is in principle easy because you just map the problem to finding the ground state of the Hamiltonian. But it turns out that after you do that, then you find that you're confronted by the issue that finding the ground state energy of a two-local Hamiltonian is hard, even for a quantum computer. This is this QMA computer. So that's not great. This is kind of a worst case scenario. So it might be that our Hamiltonian is more simple, but it turns out that, for instance, for atoms in free space, this Hamiltonian is actually an XY model with alternating sign. So with interactions that are alternating sign of alternating sign, which looks like a frustrated Hamiltonian, which looks bad. Okay, so I cannot, these statements about complexity, I cannot prove that it is hard, but it is expected to be hard. So then it looks like we haven't done anything because you cannot diagonalize this by brute force. Then there are also, some results that tell you that generically is a hard problem. So have we done anything at all? And the answer is yes, because now that we have mapped the problem into finding a ground state, we can take all the tools that have been developed for Hamiltonian problems and use it for this problem. And it turns out that people have thought about this type of problems a lot. So in particular, the thing that we can do is to, let go of trying to find the exact energy or the exact decay rate and finding just bounds for it. So the first thing that we did is to find a lower bound. So, even from undergrad, we know that you can use a variational principle to find upper bounds on the ground state of a Hamiltonian. So for us, when we flip the sign, this becomes a lower bound. Then you have to work harder, but there are methods to find lower bounds to ground states. And for us, this becomes upper bounds. And for this, we use quantum approximation theory. So there's a whole field related to Hamiltonian complexity theory on whether if you have a ground state that is generically perhaps entangled or very likely entangled, how well can you approximate that energy of that ground state via a product state? Okay, that's like, there's a whole thing about this, which I actually didn't know anything about, but I learned the last year. And then we can use these tools to find this upper bound. Yeah.
And when it's an isolated state, you're approaching it from below.
So actually for the upper bound with these variational ansatz, so let me just go to the ground state part of the, if we just look at this side of the block. So for the upper bound, this variational ansatz will also be a product state. I mean, you can come up with something more complicated, but the easiest thing you can do is to try a product state. And we actually tried both product state and entangled state, and they give the same scaling asymptotically, except for some prefactor. And we care about the scaling with n. So, and then for the lower bound, what they use actually is a product state. It's the optimal product state. This gives you an error that is a factor. You know that you're setting a bound that is the true state energy. So you're approaching it with a bound that is 6 times that obtained with the best product state ansatz. You don't know which is the best product state ansatz, but you know it exists, basically. And it is a product.
And it's below?
Yes, it's below because this is called this relaxation of ground state problems. So basically what you do is you have this, it's not exactly the same, but you have this kind of upper bound. And now you relax the constraints of maybe the state being physical. And that guarantees that you have a lower bound. So the first person that I know of that did this is actually Anderson, where he had it was some sort of condensed matter problem. And then the idea is you have a Hamiltonian, it has a bunch of terms, and then you kind of bound each term locally. And then you are guaranteed, because of the particular case of this Hamiltonian, that this will give you a lower bound. I can tell you some references about this. Yeah, I also never heard of this. I mean, there are, so this is a very, in my opinion, a quite sophisticated or quite recent field about this finding this lower bound. People have used this in the context of something called semi-definite programming, which is you are trying to find some optima of some problem. And then if it's very constrained, that's hard. And so you relax these constraints and you find this kind of lower bounds easily. And then the other thing that I wanted to say is you may find also lower bounds by forgetting about this quantum approximation theory and then just using something that is called the Engels-Goring circle theorem. So this is a theorem that just tells you give me any matrix, and I can give you a spectral bounds or bounds on the spectrum. And this works for any matrix. The problem is, and this is the first thing we did, it turns out that this bound is not tight. So, yeah, exactly. So then we got some bound that we were very happy with, and we were about to write a paper, but then the very smart student that works with us, I will tell you his name later, Larry, was like, well, actually we can do better. And the way to do better is a bit more sophisticated, and it involves this kind of things. So I actually, because Cosimo, my postdoc, Cosimo Rusconi was here like a few months ago, I didn't want to get into the details. I have slides about the details. If you want, we can go back to this discussion after, but I'm just gonna show you the results because we have like some new results and I thought this was perhaps more interesting. But basically we work a little bit. The lower bound we can get in like half a page of algebra. It's actually very trivial. The upper bound is actually trivial once you find how to do it. And I thought there should be, oh yeah, okay. And so then the last thing I want to say is if these two bounds are tied asymptotically in the scaling, then we find a scaling loss. Okay, that's the whole idea. And it turns out that there is a very large class of systems for which this is true. So then when you put everything together, we have a lower bound where R star is, well, some expression that S is like the sum of all diagonal terms of this decoherence matrix. But if we impose the localized decay, which is basically telling that the eigenvector associated to the largest decay transition, the largest eigenvalue, is delocalized, so it has support over a large part of the system. Then we find that R star, the maximum decay rate, is larger, guaranteed to be larger than N gamma max over 4.
So
and
they
then
localize, like how large has to be like.
We have a statement about the variance of this distribution of the eigenvector, but it's basically for translational invariant systems, this is trivial. And then even if you have some disorder, it should also work. So we have, in the paper, we have a statement about how large it needs to be. It basically fails if you have something that is very localized. If you have a disorder system and there's under some localization, for instance, it's not guaranteed that. So, and that typically gives localized states. It's also not obvious that super radiant states, which are this type, are also localized in the presence of a lot of disorder. So the situation where we have a lot of disorder is still under exploration. And then the upper bound, for the upper bound, we use this recent result of Bravi et al., which is they actually take they look at two local Hamiltonians that are traceless, to which we can map our Hamiltonian, and then they find this statement about the ground state energy being, or the largest eigenvalue of the Hamiltonian being bounded by 6 times the expectation value of the eigenvalue. And then you do a bit of math, and you end up with the upper bound written up there. And so both of these two bounds depend on n times the largest decay rate. And if we don't care about prefactors because we only care about the scalings, this is a scaling law, basically, which is written there. And it is universal. Yeah.
Can I ask you again? So so this would definitely depend on gamma and on this collectivity, right?
Yes.
Are you considering which case now?
Nothing. It works for the only thing that I need is that this matrix is positive semi-determinate.
For example, are you saying that if I have everyone with everyone scale with n squared?
Yes,
right?
correct.
And so why do you get an n there?
N and gamma max is, this gamma max gives you n. So gamma max for an all-to-all connecting scales with n, right? Because the trace of the gamma matrix has to be present. It has to be n.
And so you're saying that generically that's the case, so it's always n squared.
No. For all to all, this gamma matrix is 1, 1, 1, 1, 1, 1, 1, 1. When you diagonalize it, you get n squared. You cannot go beyond n squared, but you can go definitely below n squared. You cannot also go below n. So everything is bounded between n and n squared. And then you give me you have some particular system you care about. You build your matrix. You diagonalize it, which is you can do in order n squared or order n cubed, and then you find the maximum decay rate in your system.
When like in the case where you are very far, and then pairs are very far from each other, so
Then,
go below n, so they become individual.
no, you cannot. If they are individual, you have always the n, because this is the decay. So the decay rate per particle is constant. right? So if you have now all particles excited,
You are summing over, okay.
exactly, then you get always this n.
Okay,
So if you put a detector and you count photons,
yes.
you would count n times more photons if you have n particles than if you have
Even
one,
though they are
even
independent.
though they are independent.
So this n is doesn't basically has nothing to do with correlated decay.
Oh, I'm gonna get there in a second. Yes. So then maybe following with this question, we can check, do a sanity check with this scaling law. So if we have non-interacting particles, the largest decay rate is one of the diagonals, which doesn't scale with n, so it's of order 1. So the largest decay rate possible is n, is scaled with n. Now we go to the case of the cavity, and then we get n squared for the reasons I just got it. And that actually gives you another way of thinking about the n squared scaling. That is not just mapping this to a angular momentum ladder and computing. One end you get from the fact that this happens at half excitation density. So actually our bounds obtained with the lower bound with the variational ansatz, this is optimized at half excitation density. And the other end comes from the all-to-all interactions, from the range of interactions. And then, as you said, what happens with correlations? Do they matter? And they don't. Like this scaling is completely oblivious of entanglement. It doesn't mean that your state of largest decay is not entangled. It just means that you cannot infer anything about the entanglement from the scaling. And then the first time that I learned this, I actually became depressed a bit. Because I thought, oh, everything I do is trivial, entanglement, whatever. But now I have a way of thinking about this, which I can tell you, I mean, some insight. I'm not saying that this is the only way to think about it, this is the way I think about it. The first thing is that this Hamiltonian is too local. So too local means that it has support each term, it has support only on two particles, I and j. Okay. So you may have a very complicated, very entangled state, but every term in the Hamiltonian just cares about the reduced density matrix of two particles. So then you're not really probing very much the entanglement structure of that state, at least not every piece of the Hamiltonian is doing that. So that's one first piece of insight. The second one, it only applies for permutational symmetric states, which are like, for instance, those in cavities. So it doesn't apply to the generic, more arbitrary systems. But it's useful to know, which is a quantum definity theorem. So quantum definity theorem says the following. You give me a permutational symmetric state, and I just look at the reduced density matrix of two particles. I cannot distinguish that state from a product state. Actually, the overlap causes 1 minus 1 over n. So in the larger limit, there is no way of knowing. And somehow, this is what this two local Hamiltonian is doing, piece by piece. So basically, the entanglement would appear in the prefactor. It doesn't appear in the sphere.
But if I want to keep track of the dynamics.
Oh yes, so this is literally an upper bound on any quantum state that you can prepare dynamically or otherwise. So this doesn't mean dynamics may generate entanglement, may be super complicated. I'm just giving you a bound on anything you can prepare dynamically. So the key of this work is to track the specific dynamics may be super hard. To solve your specific system may be super hard, but let's just kind of zoom out and make a statement that are easier, about something that is a bound, but that applies very broadly.
And there are ways of going beyond, like there's some no-go theorem. What are the this is really under some conditions
of Markovianity mostly.
This in that beyond Markov you can get beyond.
If you think about the Markovian dynamics, I really don't know what to do. That's maybe something can be done. I don't know. You can start thinking about other.
And this experiment by Arno that they were shown in this.
I don't think the super n squared is real. I think they just got it from some very small n.
No, yes.
And I think they also know that because they have an appendix saying, I mean, the whole paper is n to the 2 to the 6, but then they have an appendix saying, well, it would be for longer, we go back to n squared. And then, so you could start thinking, what about other quantities, right? Like imagine that now I care about the decay rate of the coherencies or the decay rate of, then you could start applying the same tricks. But then the problem is, if you, for instance, want to know how a correlation function decays, so imagine that you care about sigma plus I, sigma minus A. How does this decay? You can probably still do something, but the Hamiltonian naturally becomes too local. So then you have to deal with this. And then I feel that at some point, entanglement is going to start mattering for the scaling. So, or you could try to generalize it to, to fermions, to interactive bosons. So there are obvious extensions, and I think some of them may be easy and some of them may be very hard. I think no Markovianity is on the very hard.
Yeah.
Because you don't even have a master equation to begin with. Okay, so then now that we have scaling laws, let's use them for arrays in free space. So it's very easy, the problem is you take these arrays that are ordered lattices with lattice constant small d of different dimensions, 1, 2, 3, in 3D free space, okay? Then I build this decoherence matrix or dissipative matrix, which is trivial because it's vacuum, so it's just given by imaginary part of the Green's function that has this form, okay? 1 over r, 1 over r squared, 1 over r cubed, and it has this oscillating part because it's a wave that propagates, okay? This Green's function, what is describing is propagation of the field in free space, so it has this e to the k r, which gives signs and both. So then the only thing I need to now know is how does the largest eigenvalue of this matrix scale with n for different dimensionalities. And so I could just have brute force approach, build my matrix, diagonalize it for different n's, and find the solution. But it turns out that you can be a bit more elegant than this, and you can find an analytical scaling. And so the way of doing that is the following. We're going to first try to understand the problem of the decay rates in reciprocal space for infinitely large systems. So it turns out that you can write the decay rate in K space, and for a 2D array, it has this form, okay? So this is the Brillouin sum of an infinite 2D array, of course. And you see that there is a region in K space that is actually corresponds to the light line, which is now a circle in 2D, where there is a divergence, okay? When K equals K0, where K0 is the resonance frequency over the speed of light, this expression diverges, which means that for these modes, there is very large decay, in particular for an infinite array, is infinitely large decay. Okay, this is all single particle, second line, super easy. So then what you can do is to think how to connect this physics of infinite arrays to the physics of a finite array. Well, a finite array, what it does is it samples regularly the reciprocal space with as many as n points. So now, for instance, for 2D, along one axis, I have a Brillouin sum that extends over a range of this minus pi over d to pi over d. And I'm going to have a square root of n points for a 2D array that is going to sample every axis. So then what I do is I want to see how close I'm getting to this divergence for a finite array. So I take k and I approach this to k0 minus epsilon. And then epsilon, the error, I take it as this fine grinding of this reciprocal space. And from there, I get that for a finite array, the largest decay rate is expressed as n to the 1 over 4. And so I do the same for 1D and 3D, and I get the same, these scalings. So in 1D, there is no divergence whatsoever. In 2D, I already explained, and in 3D, it diverges faster. So then I put it all together with the scaling law that I derived before, and then I find that the largest decay rate for a d-dimensional array goes as n to the 3 over 2 minus 1 over 2d. So this means that, for instance, if I build a chain of atoms in free space, even though they are interacting, they behave as if they were not. Okay, the largest decay rate is the same as if they were completely independent particles. As I scale up the dimensionality, effectively in a quantum optics language, this is like increasing the optical depth. So there is more potential for constructive interference, and this leads to these larger decay rates. And then this scaling is actually independent of short scale features like the geometry of the lattice, the polarization of the atoms, and so on and so forth. And it is also robust to reasonable disorder, reasonable as the disorder that you would find in an experiment. So if now I disorder everything such that I have just a fully disordered cloud, this doesn't hold. It doesn't mean that we cannot obtain a scaling loss for that system. I just cannot promise that it will be this one. Okay, so then we checked whether this is correct, doing some numerics. So we actually, once we have basically this problem mapped into a classical Hamiltonian, we can use this idea of mapping the problem into a semi-definite program, which is again a technique that is used in optimization. And we want to find the largest decay rate. And then we have basically an estimate of the asymptotic decay rate versus the rescale system size that we obtain, this rescaling law analytically. And you see as that n increases, everything collapses to the line, which means this scaling law are correct. Or that's another hint that we're not lying, basically. Okay, so then you may think, as actually Alejandro asked, what happens if you now take these particles and you separate them very, very far away? It also makes sense. It makes sense that these scaling laws do not hold, they break. Similarly, if you compress all of your array to basically one point, you should go back to decay. So also the scaling laws should break. So how do they break? So to do that, we really took now the systems, so we built them, in the computer, and we did numerics. And so this is a plot for the scaling of the largest transition rate into the alpha. So this shows alpha versus lattice constant. In that side, we are reducing the lattice constant, so we should expect decay-like behavior. So alpha should approach 1. In this side, the lattice constant is becoming very, very large. This is in log scale. And so we should go back to non-interacting. So alpha should be 0. And we expect that there is some range at which the curves that I'm going to show you in a second settle into the analytically predicted exponents that are marked with lines. And so then we fit up to arrays of 60,000 atoms, and we obtain these results. These shaded areas are the 1 sigma confidence intervals of the fit. And you see that indeed, if you make the system very small, it goes back to this decay-like behavior. You make it very large, it goes back to non-interacting. And for a large range of lattice constant that are also physically relevant or interesting, they settle where, this scaling settle where they should. One thing I should say is that on this right side, there are all these very nasty spikes. And it's also shaded in gray. And it means there are 2 comments there. First thing is that the goodness of the fit is very bad in this region. So basically the trend is meaningful, but the spikes are not. And now the spikes. Do we understand them? Actually, yes. These come from unclap processes that appear in crystalline lattices. So we can identify actually each of these spikes. But it turns out that when we make the lattice larger and larger and larger, then suddenly one additional momentum or unclap process now fits, and this kind of brings our fit crazy. So it kind of gives you this spike. Okay, so I don't know if I saw a question over that. Yes.
Sorry, when you said that it's independent of the geometry of the lattice,
yes,
I have a question, because if you have a disordered array, you made this argument about equally probing the fish relevant zone.
Yes.
And if it's, this is
it's true for order array.
For order arrays. So maybe if you have a disordered array.
Yes, I said that if it's fully disordered, I don't have any comment about it, because we would be able to obtain your scaling laws, but I don't know if they are this. And precisely one of the reasons is that. Another one is I don't know if the largest the eigenvector associated to the largest transition rate is delocalized. So it's the first thing that we need to study. And then from there, we can probably numerically just find this scaling of gamma max. We can also use random matrix theory for Euclidean matrices, probably, and maybe from there to get something more analytical. What I meant by it doesn't depend on geometry of the lattice is that this is for a square lattice or cubic, but if I now make it triangular, hexagonal, whatever the hell, very similar plots are obtained. Okay. Again, it would affect the prefactor, it doesn't affect the scale. Okay, so yeah, which is precisely what I just wrote. Okay, so then maybe a few comments. The first one is that you see there is this crossover from from collective to non-interacting. And I want to highlight that this scaling law, the analytical one, actually in principle apply for arbitrary systems, for arbitrary n's. But you need to get to large enough n. And it turns out that for, in this region, the number of atoms that you need, if you extend the lattice, scales as d to the 6. So you have to basically, you need, if you separate your atoms, you need an enormous amount of them to go back to this kind of collective behavior where these curves will kind of become horizontal. Of course, at some point, Markovianity, retardation starts mattering, and this you cannot obviously take this directly. And this collective is actually, if you think about experimental systems like Rydberg arrays into D, for optical transitions, and considering their distance of around 7 microns, they are placed around there for 2D arrays. So it means that correlated decay is not very large for these systems. On the other hand, as they scale up, or if they want to bring the atoms close to make faster gates, they may start to get in trouble. And even in that case, this is the worst case scenario. You're not guaranteed to hit these very super radiant systems. Okay, so then one thing that we did is we went and checked if in the literature there's been, scalings that have been obtained for several problems and whether they obey our scaling laws. And the first thing we did is we checked with a paper of the group of Susan Yelling where they look at the superradiant burst of 2D arrays, and they see that as the distance between the particles decreases, they find that the scaling is n to the 1.22, which is below our predicted one, that is n to the 1.25. So that's good. On the other hand, we looked at this experiment that I mentioned of Antoine Brouet's, and they see this scaling in the intensity that is n squared. And so we were like, oh wow, we're done. But then there are two caveats. The first one is this is a disordered system. So then our scaling laws do not hold. So this is a completely disordered plot. And the second thing is that, and this is very important if you are an experimentalist, I don't know if you hear that, it is very different to look at the decay rate of a state and the radiated intensity. So if you integrate overall angles of emission, the decay rate is exactly the integrated photoemission rate, which is the intensity. But if you just look at a small angle, you can violate this bound, and you can get intensities that basically scale at n squared. And this is also what happens in this case. So anyway, so basically this doesn't contradict our scaling laws. Okay, so then maybe some kind of take-home messages and open questions. This scaling laws set an upper bound to the decay rate of any state. Also, those prepared obviously dynamically. Some questions, natural questions, is what if you care about error correction? In particular, we have shown that in 2D you are not protected from correlated decay. On the other hand, this is the worst case scenario. We know that generic or states, as in hard random states, if you pick a state randomly from the Hilbert space, it doesn't decay superlinearly. And other questions, what do these scalings imply for driven dissipative phase transitions when you take the systems out of the cavity and you think about extended systems in free space? And also, if you think about metrology experiments such as clocks or spin squeezing, there may be geometries or even interrogation techniques where the coherent interactions are maximized while decreasing the potential of correlated decay. And the last comment is, one interesting thing is what happens in fully disordered systems. And that's kind of in our immediate list of to-do things. Okay, and then maybe briefly, I just want to show you some recent results on a situation where actually correlated decay is pretty awesome. So this situation is the following. Imagine that you have particles, atoms, for instance, in a situation where there are multiple decay. And these particles can decay to each of these ground states at different rates, and there will be one that will be dominant, which for us now is gamma 1. Okay. And because this problem generically to find the dynamics of such a system is hard, when you don't have symmetry, and we wanted analytical results, we solved it in the case of permutation symmetry. So basically, if all atoms are in one point in free space, or if you're in a cavity. So if you don't take just two ground states, so if you take d equals 2, this you can think of the evolution as a random walk in the Hilbert space, where the states are labeled by how many particles are in each of the ground states. So we start with a full inverted system. So we have 0 particles in each of these ground states. And as decay events happen, they are going kind of like down, 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 up until a situation where maybe all of the particles are in the dominant ground state, all of the particles are in the less dominant ground state, and everything in between. So if this, in kind of the most trivial example of this, you can map this problem to Galton board, where you start throwing like particles, they do like 2, and then they end up, you start counting, and this corresponds to a binomial distribution. Okay. Turns out that this problem is not as simple because the decay rate for a given state depends on the correlations of that state. Okay, so actually it becomes a quantum mechanical problem, so it's not hard to solve. And so now, if you think about, again, the simplest decay possible for 2 ground states, the probability of finding all particles in the dominant ground state is, as I said, this Gaussian. Now I have picked that one of the decay rates is more dominant than the others, so it's a binomial, but of shifted mean. Okay. But now, if decay is correlated, what happens is this. So basically, you take this distribution, push it to the extreme, which means in most cases you get all of the particles in the dominant ground state, and also you shift the mean brutally, but also the distribution becomes narrow. And the question is, how does the mean scale with n? And that's kind of useful if you think of, generically, if you have atoms, these decay rates are given by Clebsch-Gordan coefficients. If you have molecules, they are given by Frank-Condon factors. And typically, the fact that you have these open transitions limit the use of, these quantum systems for applications. So it's good to have a way of closing the transitions and not being bound by what nature has given us. Okay, so now, how do we go about solving this problem? So again, we consider permutation and symmetric systems. We have some Hamiltonian evolution, and we have these collective operators. So now all of we consider that all of the decays can be collective, okay? They can be enhanced by the number of particles. Due to symmetry, this master equation becomes a rate equation in this population basis because the coherences are decoupled, and it looks like this, doesn't matter. But the important thing is that even though it's a rate equation, the complexity of it scales as n to the number of ground states, so it's still not completely easy to solve. And again, we want to find this some solution that is analytic. So what you do is you take, or one way of thinking about this problem is you take this evolution of a random walk in Hilbert space, and now you map this evolution into a fluid in real space by taking these variables and making them continuous. So actually this, maybe I should have rotated it, but basically you can think of the rate equation I showed you before as a continuity equation for a fluid with a velocity field that changes. And now you have to solve this equation, which is also not easy. Sadly, shockingly, it's the same equation. So the first one, it wasn't easy. This one is also not easy. It's actually worse because now it's like a PDE. So yeah. So then the last thing that you can do to solve or to find an approximate solution is, instead of solve the equation for the whole dynamics of the fluid, just assume that you have a single particle subject to this fluid motion, and that you can solve easily. And so we did that. And then we find that the dominant transition ratio, that is how many of the particles end up in the dominant ground state, is 1. Okay, the ratio is 1. Minus an error that is suppressed with a particle number, with some scaling that depends on the ratio of the different decay rates. So basically, this means in the large n limit, winner takes all. Even though you have maximum competition, even though all channels can be collectively enhanced, it doesn't matter. This is like an avalanche. So winner takes all, boom, it's all. So one thing we did is to see if we could use this for something besides, having fun by mapping this to a fluid equation. And so the problem we thought about is we thought about photochemistry. So photochemistry is a perfect problem for this. So this typically you take 2 cold atoms, you drive them with some laser into a weakly bounded molecular state from which they decay spontaneously to a collection of ground states, raw vibrational ground states. And the problem for experimentalists is that this contaminates the sample. What they want is, decay to just a single state. So we looked at the strontium dimers, where the percentage of population in the dominant ground state, if decay is uncorrelated, is around 55%. And then we applied our tools to this problem. And then we found that if only one dominant channel is collective, so if, for instance, you just address this channel with a cavity, all the population ends up in the dominant ground state as the number of particles increases. This was actually shown in a recent PRL. And this is this green line. But even if all channels are collective, the same thing happens. And that may matter in free space, in a broadband cavity, and in a waveguide. Okay, so hopefully this soon will appear in on arXiv. So maybe just some final take-home messages. I think we know honestly quite not much about the many-body regime of quantum optics. So I think it's an interesting regime to work on. Some interesting open problems that are related to this work are, most of these out of equilibrium phase transitions that I know of are studied in the context of cavities, for which I would say the systems don't have that much free will. They can only decay to a cavity, to the cavity mode, and that's it. But what happens in extended systems where the atoms can decay into many different modes? So is there order even though there is a lot of competition? What does order mean in that case? So these are questions that I don't know the answer to, but I think are interesting. That also leads to some applications. Can we have lasers without mirrors? Another one that I mentioned is this collective transition quenching. Can we use this many-body dynamics to stabilize many-body dark states? I also know the answer to that. And then I already mentioned these spin squeezing and metrology protocols in the context of correlated decay. Okay, so then just before I end, I wanted to acknowledge the people in my group, in particular those that worked on this. So these are Eric, Adishi, Cosimo, whom many of you know. And then this paper is on arXiv, and I should highlight the outstanding work of Dariel, who is student at Caltech, in the group of John, with whom we collaborated on this. And then the second part of the work, actually the authors are Stuart, and also Dariel, and it's a collaboration with Tanya. And thank you so much.
Okay, so thank you, Anna. Let's have an interesting talk. Do you have any questions?
So you said in the beginning that the Hamiltonian part. So
In this particular thing?
no, in the beginning of
Yes,
the talk,
yes.
that you could include, you will
Yes.
not include it, but you could include it.
So we can include it. So
But it does not change anything regarding the.
depends on what.
Oh.
So obviously imagine that I throw away this paper and I just have like some coherent drive. Then obviously the change of the rate of change of population is gonna be modified. So so we can generalize these laws to include both local or collective driving via the Hamiltonian, but also pumping incoherently in the Lindbladian. So you find you can do the same procedure. It's now that it is not clear whether you can call this a decay rate because maybe population is increasing, but you can compute the rate at which population changes. In the most normal situation where you don't drive brutally hard or then these scaling laws are preserved. But that also tells you what if there is phase transitions where they should occur, because if the term that now you add via the Hamiltonian or via the Lindbladian scales faster than R star, that will probably indicate some phase transition. So you can do the same. I have a slide about it, but I think it basically captures what I just said. Yeah, it's these things. So now you can add these things. Now the rate will be the expectation value of each of these terms. And then we estimate, when should they matter, when should they not, and so on. It's just that this is here to explain it in this kind of PN in context.
More questions? I do have.
Sorry, I thought there was a question.
Yeah. I'm curious in the second part about the ordered array. If you have like something like a moire crystal, something with a very big unit cell, it's still feel the same.
Well, I guess it may be hard to, I mean, then it goes back to diagonalizing, you probably need, these scalings are usually observed in the large limit, so then that may impose some additional constraint, you may have to diagonalize even larger systems, and then at some point that may be hard. Having said that, perhaps analytically you can obtain them by doing something similar to what I just did, or like if there is, you should see features, well, I think it may be possible to that. I mean, I don't see why not, but maybe it's technically challenging. You can solve for this decay rate in K-space. So now it would be this kind of reduced or mini band, like reciprocal space or regional zone. And then from there, you should be able to see if there are divergences. And then maybe you can get these divergences by just doing what I just did in the beginning.
But this divergence that did you have this 1/k squared for the 2D? This is what you were showing.
Square root of k squared minus 3.
So this is independent of the geometry.
It's independent of the geometry. The prefactor is not. So this comes from a sum of over like all this is e to the iq r or something where q is in the 2D plane, and then r it depends on the lattice. But the scaling of this, as far as I know,
Yeah.
like I won't put right now my hand on the fire, but I'm pretty confident that this.
What is the role of the gap of these adjustments in
Of the gap.
Yes.
Yeah, so if you, so for instance, if, so let me, I don't know if I'm gonna answer exactly your question, I'm gonna try, okay? So if you think about a ground state problem, right? You have like your multiple levels, like states, and then you have the ground state. And then it matters very much when you're approaching this ground state or putting a bound of the ground state, whether this system is gapped or not gapped, right? But then for us, I don't know, can I draw here? So you have, well, I don't know if you can see anything at all. What? Okay, so you have like a bunch of states, and then perhaps there is a gap or not. And in many cases, you care of doing something like this, right? You don't want to put this bound here. But it turns out that for us, we don't care if this bound is kind of complete. So we don't care about the gap because we care. So we're guaranteed. So for the kind of lower bound, which is the upper bound for us, you're always, the gap is irrelevant. And then the only question is what about the lower bound? At the lower bound, we don't care about doing a good lower bound. We may be doing here this. Actually, I'm pretty sure we are because there are multiple states that scale with n gamma max. But it may not be an awesome bound, but as long as asymptotically scales the same as the other, we don't care. Does that answer your question or not?
Yeah, I'm just kind of concerned by the fact that there are multiple states, maybe by the integral of such state.
By what?
So if there are these multiple state decays,
Yeah.
and there are extensive or what is the excessive factor of them or something like that,
Yeah.
then you could change that. No?
Why would it?
Well, because I would expect that your n that you're at the beginning would become n to some power, right? You are the n times
Gamma max.
gamma.
Yes, but we obtain this from these bounds. And but nothing in these bounds depend on the degeneracy, for instance, or on the spectral gap. Only, they may be better or worse. But the fact that we have them both a lower bound and an upper bound and that they scale the same is enough for us. So again, I don't care if I'm in the middle of the band here, let's say, or if I'm exactly here, because that doesn't affect the physics I care about. I just care that this and this scale the same, even if it's a bad bound. Even if this is a bad bound, I don't care. And here I know that the bound is not very good because it's like a factor of, 6 off potentially. So again, if you, for instance, if you, I don't know, you care about quantum chemistry, the fact that your energy that you care about is 2 electron volts or 12, may be a horrible thing. You may be super far away. But for me, I don't care. I'm willing to pay a prefactor of 200. I don't care about the prefactor. I only care about the scale. And then maybe just as a example, the only thing we can do truly like exactly is this, like we can only go to 25 atoms, and we computed whether this largest decay rate is between this upper and lower bound, and it does. Of course, I mean, I'm confident that there are multiple others. Like, I know in the case of decay, it's not just a half excited that scales as n squared. If you go up or down a few excitations, they also go as n squared. But that's not a critical ingredient in driving the bounds. But I'm happy to talk further about it. So again, like if we care about the spectral gaps of a Hamiltonian to say something about phase transitions, I understand that it's a critical thing. I don't think it is critical for the physics we care about or the approach we take.
Okay, there are no more questions, maybe you can thank the speaker again.
We can get here tomorrow, but tomorrow included, so you work about that. It's getting hard for us. Good spot. Good spot there. Good. I've got